They know, like, they release that stuff
All right, so you don't have any mastering due this week. You're welcome. There's mastering due next Monday and Wednesday, but by the end of today, you can do just about all the Monday mastering, and by the end of Friday, you can probably do all the Wednesday mastering if you want to work ahead. We'll do a group quiz on Friday that covers the stuff we're doing today. Some 4. We're going to do chapter 4, then 6, then a test, then the very last week of class is 11.
So the last test is going to be on 2 chapters?
They're 2 really big chapters, though. All right, so we'll start off with a little bit of review, and then move. I don't have your test for you if you guys are concerned. Not everyone has taken the test yet, so I will have them back on Friday, because by Friday everyone should have taken it. So chances are I'll have it posted on Mastering before Friday, so I'm guessing by this afternoon, tomorrow morning, it'll be posted on Mastering, and then you'll physically get it back on Friday. All right, chapter 4. We'll do a little bit of review, and then today, you're going to need calculators. Get your calculators out. Today, chapter 4 and chapter 6 are math heavy, which is why I kind of lump them together. Oh, sorry. 16 terrible tasting pancakes. Yeah, right. All right, so we did a very similar problem, 2-3 lectures ago, right? If you have a recipe and it makes 16 pancakes, and it includes 2 cups of flour, 2 teaspoons of baking powder, 2 eggs, and some milk. And I know that makes 16 total. I'm saying that right? So a recipe is really just a chemical formula. I know I have these things, they're my reactants. In the end, I'll make 16 pancakes as my product. What if I only have 1 cup of flour? How does that change everything else? We have to divide everything by half, right? So I'll only use 1 teaspoon, I'll only use 1 egg, I'll use half a cup of milk, and then how many pancakes will I make? 8, right? So if I change that to 1, this has to change to 8. I still have tons of baking powder, I still have lots of eggs, and so these guys, I have an excess. I have lots of it. I could have used 2 teaspoons and 2 eggs. I just didn't need to. This guy right here, if I change it to only 1, this is now that is the guy that limits how much pancakes I can make, how many pancakes I can make. Better grammar. Right, so this is the limiting reagent to how many pancakes I could possibly make. Everybody else is in excess. So, extrapolating that out to more chemical systems. That should be nice. For molecules, we use balanced chemical equations, which is kind of what this is, right? It's kind of like a balanced chemical equation. We're going to use a balanced chemical equation. From which we can predict amounts of product made. So if I know how much I put in, I can predict how much I should make in the end. All right, so let's say I have this reaction, right? 2 hydrogen gases combine with 1 oxygen to make 2 waters. First question, is this balanced? Yes, okay, good. So first step from here on out is going to be, is this equation balanced? Otherwise, everything you do from there on out is going to be wrong. First step, make sure it's balanced. All right, so from this equation, I can say the following, right? All right, so in words, so from this equation, if I want to make 2 moles of water, I have to have at least 2 moles of hydrogen and 1 mole of oxygen to make that. Just like in pancakes. I have to have all those ingredients all lined up in order to make my 16. All right, the coefficients, which are all right, that's the big number in front. These guys right here are the coefficients. Right, they tell you the mole ratio. They tell you 2 to 1 to make 2. So if I put in 2 moles of hydrogen and unlimited amounts of oxygen, how many moles of water can I make? 2. If I start off with 6 moles of hydrogen and unlimited oxygen, how much water can I make? 6, right? So if I put in 6 and enormous amounts of oxygen, I can make 6. What if I start off with unlimited hydrogen and 1 mole of oxygen, how many waters? So if I have tons of this, just 1 of these, how many of these do I make? 2. What if now I have 2 oxygens? Right, what if I now have 6 oxygens? 12, right? So we are now going to use these coefficients as a conversion factor. All right, so now we're ready to do some calculations. Yeah, Justin.
All right, like with the chemical equation, how you have behind the H2 gas and the O2 gas, and then
Yep.
you end up with liquid.
Yep.
All right, how would we know if it's going to produce a liquid or a solid? Or...
You don't know yet.
Okay.
Next semester, you'll know. But for now, I'll have to give you those. Yeah. Yeah, we don't know enough chemistry yet to predict states of matter. Yet. 109. You'll be able to predict states of matter. Yay! All the useful skills you get. All right, so the question is, when we are making a compound, how much can it produce? Using my snazzy balanced chemical equation, we can figure that out. So here's what I want to do. Here is my question. All right, so if 60 grams of calcium fluoride is reacted with unlimited amounts of sulfuric acid, how much HF can be made? All right, these are going to be the 4 steps we need to work through. So the first question you have to ask yourself is it balanced? Good, good, it's balanced. So you can check that one off. Next question is, these ratios are in moles. So for us to do mole ratios, we have to turn our grams into moles. So how do we turn grams into moles? What do I need to know about CAF2? We have to know its molar mass. All right, so let's go to the board. All right, so CAF2. Let's see, calcium is 40.08 grams per mole plus 2 times 18.99 grams per mole. Definitely be calculating at your bench also. Make sure that I'm doing the right things. My math skills have been a little off lately. Good. All right, so now how do I use the 60 grams in conjunction with this? Do I multiply them together, divide one by the other, add them together? So if I have where do I put the 78? Let's see here. How many significant figures do I get? 3. All right. Now moles of calcium fluoride. How do I get from moles of calcium fluoride to moles of HF? What's the mole ratio? How many moles of that make how many moles of that? 1 to 2, right? So we're going to use it like a conversion factor. many seven figures do I still get to keep? Still 3. Okay, now I have moles of HF. Now I want to go from moles of HF to grams of HF. What do I need to know about HF? We know it's molar mass, which is 19.99. Where do I put the mass? On the top or on the bottom now? Oh, yeah, sorry. Okay. What units am I left in? Grams of what? So now it's not good enough just to say grams. You have to tell me grams of something. All right, good. Let's do another one. No, we're not ready for that yet. Let's do all right, how do I get, what's step number 1? Is it balanced? Is it balanced? No, it is not balanced. What do I need to do? What should I do to this one? Okay. Okay. So step 1, balanced, done. Excellent. So now I need to, I'm given 25 grams of aluminum. Now I want to know how much aluminum chloride I can make. Step number 2 is finding moles of aluminum from grams. So we'll go to the board. Let's see here. Okay. All right, aluminum has a molar mass of 26.98. I just made the problem up off the top of my head, so everybody double check my math. I think this should work out. 3, 2, 7. Woo. Yeah, okay, good. All right, how do I convert moles of aluminum to moles of aluminum chloride? That sounds very exciting. All right, so if I put in 2 moles of aluminum, how many moles of aluminum chloride do I get? 2. It is, and you don't have to show the math, but it's a good habit to always write it down, just because it won't always be 1-to-1. Just like you don't have to show me 3 different steps. You could have done this, times the molar mass again, all in one step, And that's fine. If you are more confident doing it one step, not a problem. All right, so then how do I get moles of aluminum chloride into a mass of aluminum chloride? I know the molar mass. Let's see. I'll have to. Okay, so what I say, aluminum is 26.98 plus 3 times 35.45. 26.98. 3 times. Anyone check my work? Is that right? Okay. Anyone not get that? Anyone actually check me? You guys are very trusting. Emily's not trusting. I appreciate that. Yeah, don't trust my math. All right, how do I feel about those? Pretty confident? Questions about doing it that way, starting off with a mass, finding the new mass using the equation. All right, and I guess we're going to take the level of challenge up one notch. And talk about limiting reagents. All right, when carrying out a reaction, it is often the case that the reactants are not in the exact mole ratio that you need. One will be used up first. Right, so in my pancake example, wherever that went, the limiting reagent. Here we go. Right, if I only have 1 cup of flour, that's the thing that limits how much I can make. Same thing, the one that gets used up first, that's the limiting reagent. That is the compound that's preventing me from making as much as I possibly could make. And then everybody else will be in excess, which we call the excess reagent. Nothing clever about that. So let's walk through a limiting reagent problem. Let's see here. Okay, so these are the questions I want answered. All right, given 856.0 grams of glucose and 532 grams of oxygen, we need to figure out which one of those reactants is the limiting reagent. It's just my hand, so that way we're not slowed down by doing the molar mass calculations. All right, so how we solve limiting reagent problems is very similar to what we did for the just regular problems. First question always, is it balanced? It is, right? Definitely balanced. Okay, good. Now you can do this in two different ways. You can either do it all together or you can do it by steps. But the second thing we need to find out we want to figure out how many grams of carbon dioxide can be made starting with the glucose, and then how many grams of carbon dioxide can be made starting with the oxygen. So we're actually going to do the same problem twice, starting with different molar amounts. So how many grams of carbon? So, just like we did 5 minutes ago, we're going to do the same 3 steps. We're going to find the moles of glucose, find moles of carbon dioxide, convert that to grams. Then we do it again. Then we do it for the oxygen. Find moles of oxygen, moles of carbon dioxide, grams of carbon dioxide. And we'll see who makes the least. And whoever makes the least is our limiting reagent. So I'll give you guys like a 2-minute head start. You can certainly double check with the people around you. I get somebody who matches that? Okay. So, which starting product makes the least carbon dioxide? All right, comparing these two, oxygen makes the least, right? The glucose makes over 1,000. This guy makes only like 700-ish. All right, so that'd be the end of that question. Oxygen is the living region. That's all they want to know. Yeah.
Would you have to convert to grams or could you just go?
You can stop at moles. That'd be fine. Yep.
Wouldn't you have to check for H2O as well?
You do not have to.
How come?
Because whichever one's the limiting is going to make the least of both. So I could have chosen water or carbon dioxide. It'll tell me the same information. All right, ready to do another challenge one? Take that and add one thing onto it. I mean, you can see that the math isn't hard on these. It's just the thought process of walking you through, remembering to do all the steps is the tricky part. All right. And I'll try going this way. I took this one off mastering, so hopefully we'll finish it and you'll have one homework question mostly done. All right, so they give you this. They give you an equation, and they give you moles of starting product. And the first part of the question is how many moles of carbon dioxide can be made with both of these. First thing you have to look at is it balanced? No, not even close. All right, take a minute or two. I'm going to say all the coefficients are greater than 1. There's no 1s in there. And do this guy last. Do the oxygen last. haven't balanced it yet. I'll give everybody a hint. This is a 2. Now, this is a 2. What does the carbon dioxide have to have? It has to have 16. Now, if that's a 16, and this is still a 2, what does this guy have to be? 18. What's this guy? 25. Obviously. Right? I mean. All right. So that's part 0. All right, part 0 is making sure it's balanced. You can't even start the problem until you've done part 0. All right, so then the question is, how many moles of carbon dioxide can be made knowing I have this balanced chemical equation? Which one do you want to start with? The C18 or the O2? Well, let's do them in order since no one has any preference. Okay. Okay, what number then do I put on the top of this? If I'm talking about carbon dioxide. Or if I start off with moles of this, what do I put on the top of this fraction to find out about carbon dioxide? Where I put the 16 for 2. All right, so let's see what that turns out to be. 0.4 times 16 divided by 2. Okay, let's look at the other one. All right, now what number do I put on the top compared to the bottom? What goes up here? All right, the 16. And then what goes down here? 25. Which is why I always write out these fractions, because sometimes they're not. It's harder to do in your head. Times 16 divided by 25. All right, so which one tells me how many moles? This one, right? This is the limiting reagent. So that is as many moles as I can possibly make. That's it. That's the limiting. All right. Part 2 to this question. Is how much do I have left over? All right, so this is going to be thinking backwards. So if this is as many moles of carbon dioxide that I can make, I want to use this number and go backwards, figure out how many moles of octane I would need to make that many moles of carbon dioxide. All right, the minimum amount. So if I can only make as many moles as this, how many moles of C8H18 makes this many moles of carbon dioxide? So do the problem backwards. So we're going to start with this. And I want to end up in moles of C18, or H18. So I put the moles of carbon dioxide, the 16, on the bottom. And I put the 2 moles on top. So let's see, how many moles would that be? 0.557 times 2 divided by 16. So I only need 0.069 moles. Yeah, question.
Could you do the 3.2 minus 0.557 and convert that to moles? Like, take it,
You mean do the mole difference?
like, you see how many moles of whatever could be made by the octane
Mhm.
minus this stuff from the oxygen, and then you have that much CO2. Like, could you convert that much to octane to CO2?
No. Mm-mm. No, because the difference here doesn't tell me how much I needed. It just tells me how much was in excess, so you'd be doing an extra step.
Is that what we're finding for the?
We're finding how much extra of this was left over. Yeah. Yeah. All right, so I only needed this much. How many moles of octane did I have to get started? If I only need this much, but how much did I put in there? I put in 0.4. So how do I find out how much is left over? Subtract. So that's how much extra I put in there. Does that make sense? We will do more of those on Friday. I don't have enough time to do one more. So we'll do more of those on Friday and then talk about percent yields. So my thought for Friday, because it's Halloween, I do love Halloween.